Hello, everyone. Today we're going to talk about enterprise systems and some of the nuances and the differences and the various types of enterprise systems that we encounter in industry today. There are various types of systems, as you all can imagine. Information systems. We've been talking thus far in our discussions about the components of systems, how systems interact, how systems are built. And I think it's a good time to level set the variety or disparity of systems that actually make corporate America and really global business work and enable billions and billions of dollars of revenue to be managed, businesses to flourish, and information to reach our hands, even as in a simple device or seemingly simple device as our smartphones. So enterprise systems come in a variety of complexities. The most basic type of a system used by large-scale enterprises, notably, are transaction processing systems. We also have resource planning systems, or also called ERP, Enterprise Resource Planning Systems. Data warehousing, which we started to discuss in our last session. Data warehousing differ from transaction processing system in that they are largely used to create optimal data stores and optimal data access points to do analysis and to store historical information and that sort of thing. So they're optimized for a different use than day-to-day real-time transaction processing systems. Customer relationship management systems is a broader category of systems that came into play notably 20, 25 years ago. I had worked for a company that coined CRM, or essentially, I would say, created this acronym called CRM, and that was Siebel Systems. Siebel is now part of Oracle, and I was fortunate enough to see some of the early leading edge thinking on sophisticated CRM capability. And it was a fun time, fun job, and fun involvement with clients as well as internal product folks that develop these systems. We have a slew of systems called, or under the office automation category. Those are things like Microsoft products that we use, email, things that keep us together from a office telephony, etc. point of view. There's groupware and collaboration systems. There's, of course, the intranet, which is a company's internet solution where everything is brought together from various departments, various groups. There's automation systems. There's supply chain management systems. So these are that's not an exhaustive list here, but this is indicative of some of the large-scale enterprise systems. We also have support systems to make managerial decisions or to manage business environments, decision support, mining, geographic information systems, knowledge management systems. These kinds of systems are in the category of what we call managerial support systems. So today we're going to focus more on the top list of systems and really some of the tricky points and how they are built and how they work. The first basic concept in an enterprise system is that of processing. How is data processed? You have really two modes. There's batch processing and you have online, or what I would say more real-time processing. Batch processing is let's say, a system that uses batch processing is one that queues up the transactions and processes them at one time. An example of this could be all of your banking records, right? If you had several deposits and withdrawals, you will sometimes see those transactions as pending, and every so often they clear and they go through a cycle, and usually it happens overnight or in, a 2-day window. That might be an example of how transactions in the banking world get batch processed. The key disadvantage, obviously, is there's a time delay. Not everything can be afforded to be batch processed. For example, aviation systems that are tracking landing and takeoffs and managing air traffic control obviously would not function very well in a batch environment. So a very simplistic look at this is where transactions come in, there's some sort of operation, those transactions are loaded or queued up. Then every so often, periodically or under some event, they get processed by a computer. Maybe there's some cross-referencing with some master data files for reference information. And then a result is created. Either it's a report or a screen view or what have you. Online processing, on the other hand, is either interactive or it could be inline system processing. This is where like a transaction's entered directly when it occurs, it's processed. The same reference information might be looked upon in master files by the computer, one or more master files, and then processing has taken place. So uh, many times there's a combination going on where there's some online processing that a system does and some batch processing. Um, Obviously, there's delays with batch, like we've just mentioned, and online is generally instantaneous or near instantaneous. Batch processing tends to be less expensive on computing resources. Also, there isn't a perceived delay of time. Everyone knows there's an expectation, there's a service level that these transactions are going to be processed in a certain amount of time, or they're going to be reflected on an account in a certain amount of time. So users are expecting this delay in general. They might not be happy with it, but they might expect. I know that when I see pending transactions on my online view of my account, I rather not see them pending. I rather see them closed or completed. So there are obviously pros and cons, and there's a reason many times batch is used, because sometimes the data available to it that it needs, like those master files, may be updated at a different time than when the transaction took place. So you couldn't actually finish the processing unless those files or that information is available. So there are operational reasons why you would want batch or need batch. And of course, there's trade-offs, as we've discussed. Now, a system performs one or more functions, and generally those functions support a business environment. By the way, the scope of our discussions in this class and in this series of videos is always on enterprise or business-oriented systems. There are systems that serve a variety of other needs besides business and commercial needs, but for the most part, the references in our work that we do in this in this class is going to be limited to or in the context of business. So there are various business functions, as in most businesses. You see these common functions like marketing, accounting, personnel management, engineering, planning, forecasting, sales. These are common functions. And needless to say, there are enterprise systems in every organization, even the most rudimentary organizations now, that support each of these areas. And of course, things like ERP cross areas, right? They are intended to go across multiple departments and divisions. And so sometimes that works very well. Systems are also integrated to work and be effective. For instance, sales data produces sales, and sales generates invoices. Invoices are summarized, and there's maybe some weekly or periodic analysis that happens, and then that's fed into top-level management to determine how companies are doing, or how certain divisions are doing better than others, and it helps long-term analysis, planning, and potentially growing the business by having that sort of data and analytics at their fingertips. So, you couldn't have these key business processes enabled unless there's integration across these various systems. And of course, as you can imagine, integration makes systems complicated. That's where really the fun of systems development is. Generating an isolated system that works independent of any other system in an organization is a menial, trivial exercise these days with the technologies available, and can be done pretty much with great ease. The complexity and the failure points largely come with um, one system talking to another, or one system talking to many systems, and its ability to do that correctly, its ability to recognize data and process data, um, the receiving system and the sending system being in sync at the right time. These are areas of complexity, right, that plague systems development projects, and actually puts pressure on them to fail at. And many of them do fail. Most systems projects over $1 million of effort generally fail out of the gate, and they have to be tweaked, and um, adjusted, and maybe perhaps in many cases redone in order to achieve the business benefits that were perceived. So it's not for the faint of heart. It takes a lot of blood, sweat, and tears to get systems up and running successfully, and then, of course, when they're running, maintained properly and growing with the business. That's a whole different area that businesses tend to underestimate or underplan for. Distributed systems, you'll heard the term distributed systems. This stands for uh, uh, of a group of systems where processing power of the systems is spread to multiple sites. The internet really enables that on the most part these days. So you don't even see it happening, but it's happening behind the scenes. Um, a client server system is perhaps something that was generated or created back in the 80s and popularized. It's a type of distributed system where processing power is on a server computer, central server computer, and then you have a number of client computers, usually PCs. So distributed systems is the overall category of systems, and then client server is just one type of or one instance of a distributed system. Um, how do these systems work? Well, you've got a client, meaning a what we used to call a dumb terminal, meaning there's a computer or a screen on one end, usually near the user, where the user has access, and that client system is really only responsible for viewing or interacting with the main system. The main system is really on the server side, on the right side of this slide, which typically has the brains or the application software, um, and needs usually a bigger machine to process that. So you don't have to worry. The client machines don't have to be that strong or that demandful. Data storage is done on the server side. Group and web pages are rendered on the server side and passed over to the client. And then you have this middleware component, which is the software to support this interaction between client and server. Many times you'll see operating system act as the main middleware, right? So iOS on your phone is the operating system, the middleware that actually connects you to the servers. And in the case of smartphones, in the case of the internet, servers are distributed, right, widely. It's not just one place where you're getting your data and your processing power from. It's many servers that you don't even realize, but you're looking at it on your phone and you're seeing it. So your phone is acting as a client in that case. You have obviously different types of client-server systems, two-tiered and three-tiered. Three-tiered started becoming popular in the early to mid 90s, where you had a split out of the server components. There used to be a database server and then a application server, which was different and onto the side. And that enabled optimization and separation of this data layer and the application layer. You heard me talk about in an earlier session how application software can be throwaway, and you would want to leverage the database. And this kind of three-tiered architecture helped us do that. We can separate our design of the database from the design of the application, and in near or long-term basis, replace either one independent of the other and have them talk to each other. Generally, it's much more expensive and a much bigger overhaul to redo the database side, as we discussed, because that's how data gets accessed and stored. The application side tends to be relatively easier, especially with the technologies available. But this kind of tiered system architecture enabled that. If you can see, if we had the two-tier system, it would be very hard to split out the data, the database access layer from the application access layer. And within client server, you have a fat client, thin client concept, and a fat client, thin client, fat server concept. And this is just how the programming and the design, sometimes there are components on the client terminal that actually run for speed. And this is a trade-off between speed and processing, right? If everything gets done on the application layer, then less has to be done on the phone or on your computer or on your client side, which means you don't have to be reliant on the client technology as much. Just go through the browser, for example. That would be considered a very thin client approach. But many times you do need for example, Java or Flash software, or things like that that come to mind as an example, where a lot of the rendering and a lot of the processing is actually passed over to the client. And oftentimes applications use that, apps use that because they want to enjoy the speed. For example, rendering video and processing all of the video on the server may create latency and create a choppy video viewing experience. So for that reason, videos are many times processed more heavily on the client side, which of course then puts demand on the client computing power, making sure that it's fast enough, good enough to render a good user experience. So lots of different architectural considerations when you start to design these type of enterprise systems. I will just briefly talk about virtualization, this concept of virtualization. There's server and desktop virtualization, where server is splits the physical serving power with multiple servers, and each server can be employed as a standalone physical server, reducing the number of physical servers. Again, this is how server design takes place. Desktop virtualization is implemented using that client server model, where a virtualized desktop environment is stored on a server, and then there's a local storage of desktop device. You'll see things like VPN software, or even what is it called? Citrix software, where your computer is mimicking, your computer at home is sort of mimicking and taking on both the client and server aspects on your computer, and offloading that from the actual place where the server is stored. So most of us don't see this happening and even care about it. It just architected in a way to create a good experience from an end user perspective. Service-oriented architecture talks about application architecture that's based on a collection of commonly used and tested functions. Every function then becomes available as a service to the programmers that are using it. And once the service is created, and the service could be anywhere, it could be within your enterprise, or it could be Amazon Web Services or somewhere else that you're using these branded service modules, and they can be used over and over again. And many of them come at a per cost use, per transaction use, or a flat rate use if you were to purchase these services. In this way, the coding doesn't have to be done over and over again, and they're tested and proven. Web service is a collection of technologies built using standards like XML, which is a standard protocol of communicating on the web. And you have other protocols that are used on the web that are very common, namely SOAP and WSDL and so on. Transaction processing systems generate a lot of data, right? These are things like invoices, checks, reports, orders, many things that bills, payments to employees, paychecks. These are examples of commonly used transaction processing systems. They generate thousands, hundreds of thousands, millions of data points for every organization. And obviously these data points have to be stored and appropriately factored in into the design of the system. For example, a payroll system is a system generally used to produce checks. And, you know, there are many subsystems that make up a payroll system to make these checks come to life, essentially. For example, there could be calculation systems that are calculating people's take-home pay after deductions and after considering the salary. There are um, a matching going on with what the employee selected on their W-2. So that could be a master file record lookup in the example that we shared earlier. There's budgeting, there's a feed to accounts payable. So there's a lot of subsystems that are used to accomplish payroll. There's also examples like order entry systems. Order entry systems are sales processing systems. You many times need querying facilities. You need a facility to link to other systems like pricing systems and inventory systems. And this could be a schema here of a system schema, not a database schema, but a system schema of how an order entry system works, or the design of the order entry system, right? So you can see that systems like this tend to be complex, tend to use a lot of storage, tend to use a lot of processing power. And the good news is many of these types of systems are already made and sold as services or as packaged implementations where you can purchase systems right off the shelf and actually enable or implement them to run your business. And many of these systems now are on the cloud where you don't, they're running in a fully distributed environment, unbeknownst to you as a company owner or a company management executive. And you pay a rental fee to use these services, and then you implement them for your specific business. So you'll see that these days, many people aren't creating their own, many companies aren't creating and maintaining their own systems. They're really renting or purchasing or implementing these packaged solutions that are made by companies like SAP, Oracle, Workday, and so on and so forth. That brings us to the ERP system category of enterprise systems. These are a set of integrated business applications. Generally in the industry, they're called modules that carry out common business functions, like sales, like accounting, like um, information management, and so on. There's full support for order fulfillment. There's full support for sales. There's full support for integration between sales and order fulfillment, for instance. And the ERP systems were really the first wave of large-scale enterprise system packages. We later branched out to CRM and supply chain management and so on. Now take us back to mid 90s for a second. SAP became a strong entrant, and other vendors started to design these suite of applications where we were integrated across the board. SAP really pushed the industry in this direction and took up a lot of market share. They still have a lion's share of market share in this area, and their promise was to connect suppliers and customers and various stakeholders together with commonly used modules, tested, tried, proven. And really, I view ERP systems as the system to manage the entire business. If you have a smoking ERP system with all of the different bells and whistles of the modules and the hooks to CRM and others, you pretty much can run your entire business. You need a very, very thin IT crew than you would have needed before or otherwise. And it really works. But it has to be planned correctly. It has to be implemented correctly. Otherwise, poor ERP implementations actually weigh down on the business. Um, um, Many times companies try to do a best of breed solution. They'll buy uh, components and modules from multiple vendors depending on their strengths, right? Um, Generally, what I've seen in my experience is that's not such a great thing to do. Very difficult to manage multiple vendors and multiple solutions, very difficult to integrate. However, many of these popular vendors do not have the entire suite that works. As much as these guys have been working on it, every vendor has their strong suit, and there are strengths and weaknesses and trade-offs. So many clients actually do end up doing the best of breed, thereby increasing complexity and cost because they have to. One vendor doesn't necessarily offer a palatable or an acceptable solution in every area of the business. And many customers will buy one and build another and try to integrate and do a hodgepodge of things. Keeps us all real busy. So, for example, in the SAP suite, you have quite a bit of uh, modules that can be purchased. There's modules in financial management, human capital management, we call that HCM, operations, corporate services, end user, customer experience, analytics, and so on. You've got front office and back office modules. So you've got a really good suite of products to select and customize to your needs or configure to your needs. Oracle has a very similar blueprint, and as do many other vendors. I think SAP, Oracle, Salesforce, these are some of the top providers in today's market. Why would you do ERP systems? Well, there's clear benefits, right? You can enjoy and use modules right out of the box day one that were designed and support the business processes that you're looking to enable. They are generally easy to integrate, or they have good integration tools. These systems and modules were built recognizing that they can't stay in isolation in a particular environment. So access to integrated data and creating this promise of unified platform actually is reality now with ERP systems. So this can be fairly easily done, and the tools have gotten much more robust. The challenge is always understanding the business requirements and the data and matching it properly. And that's the art of the implementation folks that do that. And lastly, but not least, ERP offers support for global transactions. So, for example, national currencies are automatically converted and appropriately registered. Employees in different countries can see the same screen in their own languages. So there's multilingual support right out of the box. Years ago, if you wanted to build a multi-language system, you'd have to convert every screen separately by yourself, and that takes a lot of time, effort, testing, and all of this has been done for us by the ERP providers. There's infrastructure benefits. You get centralized database, you get software updates and regular fixes done by the vendor. These are things that typically IT would have had to worry about, and now they are baked into the purchase price, if you will, or the arrangement that you have with the vendors. Data warehousing is really a large data store facility, as we've been discussing, where we take all of the transactional data and denormalize it, or even maybe bring it as is, to create an environment for reporting, analysis, surfacing data quality issues, etc. Warehousing is designed for, data warehousing is designed for analysis, not efficient transaction processing. That's really the key. You're not using it to operate your business, you're using it to analyze and support your business. And a large part of the reports come from a data warehousing strategy. Every data warehouse has some key elements. There's the construction of the warehouse, there's the operation of the warehouse, and then there's the analysis and reporting, and of course how data flows in, periodic, frequency, etc. Is all design considerations for a data warehouse. Data is organized generally by subjects. It's time variant, it's integrated, and it doesn't move too much because it's done periodically. Data warehouse is generally updated in sort of a batch setting. It doesn't have real-time hooks typically to the other systems that run the business. So therefore, we can say in some sense it's non-volatile. And generally, it's read-only. People don't go updating it, so there's consistency and transparency of data. CRM, as we mentioned, is a business strategy, right? Essentially managed towards creating systems and information organized by customer and nurturing or growing customer relationships. Many companies in the 90s, maybe even a little earlier, had to redefine their systems and their processes and do it in a way that was customer centric. And we saw direct results. We saw interactions in companies that focused and had a good CRM strategy to have high customer satisfaction or better customer retention, because the interactions were focused and organized by customer needs. And CRM, just like any of the other strategies or systems, enterprise systems that we've talked about, also works on a promise of an integrated approach, right? So marketing data, sales data, support data are all connected, and users then get a single view of the data. For example, if you're a salesperson and you work for a company that has a good CRM strategy, you will know on your fingertips who from your company did what with this customer before you make a customer call. So this way you have all of the interactions and an idea of how the customer was dealt with before you even pick up the phone and speak to the customer. So you can have a much more meaningful conversation, a much more informed conversation, and therefore hopefully a much more productive conversation. There are traditional channels that CRM interacts with, and of course some of the newer channels. There are traditional channels with call centers, field reps. They all had a system, a tool to connect to customer data, right? And the new channels are email, websites, and things that come from other wireless sources. All of these are integrated together, so there's a single face to the customer, no matter which channel data comes from and which channel has interacted with the customer previously. And this is real powerful stuff. Some of the top enterprise vendors offer all of these solutions or modules out of the box, just like ERP. And they have templates for certain industries that fit. And companies like Oracle and SAP that are traditionally focused on ERP also have CRM modules that connect or work with ERP. And vendors like Salesforce.com was one of the first to position itself as an on-demand solution where it's hosting the software. Salesforce has this mantra of there will be no software that exists. And that's because they have this vision of controlling all of it or offering it as a rental rather than an ownership model where us as the end users in a company don't actually have to worry about where the software sits, who's maintaining it. It's all done in the cloud. CRM systems pull the data that's stored in a warehouse very often to provide that robustness, right? So for example, in the case of Harrah's casinos and hotels, their total reward system captures all of the guest transactions and what the guests have been doing. So the company can track who plays what games, where, when, how, and then offer special deals aimed at generating that kind of repeat business, right? So a lot of sophisticated and analytics happen in the case of CRM solutions, and it's really, really powerful. Now, every enterprise system works with a couple of key ingredients, and one of the key ingredients in designing or making sure a enterprise system will be functional and operational, whether it's packaged like an SAP and Oracle, or even built in-house. One of the key components, as we've been discussing leading up to this lecture, has been designing the database. The data and how the data is stored and accessed is extremely important. So if you were to design a database schema, you would have to approach it using some sort of methodology. And there's many ways to do this, but in brief, the first thing you'd want to do is understand the requirement. What is the system trying to solve? What is the business problem that we're trying to solve? What are the needs of the data? How is data going to be used? Which data elements are needed? Understand the full use of the data, the frequency of the data, etc. Understand the potential issues that can arise with the data, either some of the ones that you already know or anticipate. So this is sort of, I call it data risk management, right? So this has to be analyzed. You have to understand what needs to be done to use the data to create the information. Remember, we talked about data starts with bits and bytes, but we want to understand how that data is going to be used by the system that's going to consume it to create information, right? Is it going to be used to create information, or is it a pass-through system? Those are areas of analysis that are needed to building a successful database schema to support the enterprise system. Then you have to ask, well, why is the information that I'm storing in this data important? What is the end state? What decisions are being driven? What processing needs to be done? What are the inputs and output requirements? And are there usability considerations? How is the user going to interact with the data? So this is just an example, straightforward example of how I think about things when I'm designing a system and then when I'm designing a database to support the system. These types of questions answered and considered in an environment or an organization, you can then move to creating a database schema then that can support your business systems implementation. And generally, there are people that are assigned to do database work, as I mentioned. So you would work with the database team, who's of course well versed in how to do and build effective schemas. But so the critical component of an enterprise system is the database, right? And once you understand those types of questions, you can create a database schema. This is an example of a very simple database schema that keeps track of customers, employees, offices, product lines, products, details of orders, and payments. So this could be an very basic and order management system where you're keeping track of customer information that you deem as critical. For example, the name, last name, phone, address, right? You're keeping track of the orders that the customer places. You're keeping track of details about each of those orders. Then you're keeping track of the payments that the customer is making. Order details connects to products because every order is going to have products that the customer has bought, but the products also map to different product lines. And then there's a relationship between the employees and customers, perhaps who sold the order to the customer, and where those employees are located in terms of the office that they map to in an enterprise. So this could be an example of a very basic database schema. It's using database schema notations, which I'm not going to cover here. It's been covered in separate chapters of the textbook that you all should be familiar with and are reading. But there's standard database schema notations, one to many, many to one, that we've discussed in the last class. And a diagram like this is just an example of what I would expect if I asked you to create a database schema for a simple project. So this, there's no one right way to do this. It's depending on the information that you've been able to ascertain and collect from your environment. And generally it's done in waves. So you do the first wave of this, and then you revise it based on inputs in the organization, and you settle on a database schema, which then gets consumed by your business processes and systems. So hopefully this is helpful. I will close with saying that enterprise systems are extremely sophisticated and also very much used to